Hi students, welcome back to the class. In the last class we were discussing about local maxima and local minima through an example of making a cardboard box out of a cardboard sheet. Right. In this class we are going to the same topic in detail. Suppose this is a graph of a function. Right. Suppose this is a graph of a function. Okay, suppose this is a graph of the function. So you can, and let this point be x1, this is x2, this is x3, x4, and this point is x5. Okay, so we are going to discuss about these points x1, x2, x3, x4 and x5. Right. So x1, the point x1 is one of the local maxima of this graph. Right. And x2 is the local minima. So this is local maxima. This is one of the local maxima. This x2 is local minima. x3 is also a local maxima, x4 is also local maxima, and x5 is point of inflection, right? x1 and x3 local See, the x1 is said to be local maxima because we can clearly see that the value of the function is at x1 is greater than the value of the function at nearby points of x1. See, at the nearby points like this or this, the value of the function is lesser than the value of the function at x1. This is the value of function at x1. And this point, the value of the function is lesser than x1. So x1 is said to be the maximum value or the locally maximum value. Okay, in this area, locally the function is maximum at x1. But we can't say x1 is the f of x1 is the highest value because the function goes above x1 at a lot of points, right? The function goes above f of x1 at a lot of points after this x5. Right. So x1 we can say it is locally the maximum value. Like that, x2 is the locally minimum value. Since the value of function at x2, this thing, f of x2, this is f of x2. The value of the function at x2 is lesser comparing to the value of the function nearby x2, right? And let's see what happens in x3. At x3 also the same thing happens. It is comparatively x3 is value of the function at x3 is higher compared to the nearby values, right? And x4 is the local minimum. x5, let's see what happens in x5. x5 is neither local maxima or local minima. This point x5 is said to be point of inflection. Okay, point of inflection means at this point we have horizontal tangent like local maxima and local minima. The slope of the tangent is equal to 0 at x1, x2 and x5 also. But x5 is neither a local maxima and nor a local minima. Because at the point before xy it was increasing and after xy it is again increasing. Okay, so let's conclude about this local maxima and local minima. Okay, at local maxima and local minima, the function's derivative or the slope of the tangent is equal to 0 at local maxima and local minima. But the converse is not true. That means if at local maxima and local minima the derivative is 0, but we can't say that if the derivative is 0, the point will be either a local maxima or a local minima. Because at this point also, this point of inflection also, the derivative is equal to 0. Right. So the converse is not true. Okay. And let's see these points. Look at this point. Okay. So this point is a local maxima, this point is a local minima. But at this point, the function derivative is not 0. Okay. The function's derivative, what is the derivative of the function at this point? The function is not differentiable at this point. This we discussed when we were taking the topic differentiability. the function is not differentiable at point like this where we can draw more than one tangent. The function is not differentiable at there. So at this point x3 and at point x4, the function is not differentiable, right? So the local maxima and local minima occurs not only at the point where the derivative is equal to 0, it occurs also at the points where the function is not differentiable. Okay. So at local maxima and local minima, the derivative equal to 0, but the converse is not true because derivative equal to 0 at the point the derivative is equal to 0 at the point of inflection also. Okay. So now let's write the notes on this topic. Right. So write the definition which is in page number 220 of NCERT part 1. The definition of local maxima. That f be a real valued function and c be any point in its domain, any interior point of its domain. C is called the point of local maxima if there is an h greater than 0 such that f of c greater than f of x for all x since upper interval c minus h and c plus h. So there must be an h which is a positive value such that f of c is greater than f of x in all interval c minus h c plus h. So suppose this is the point C. Okay, suppose this is the point C. And let's create an interval, open interval C minus h and C plus h. Okay, suppose width of the stop is h. So then this will be C minus h. So this is C minus h and this, if this is h, suppose this width is h, you can see the top, the red top, this is h. So this is C plus h and this is C minus h. Now we just create an interval C minus h, C plus h. So open interval C minus h to C plus h means from here to here. Okay, so we can say the C is a local maxima. The C is local maxima if f of c greater than f of x for all x in C minus h and C plus h. So we can clearly see this C, the f of c means the value of the function at c. This value, this is f of c. So we can clearly see that this f of c is greater than all values in this interval c minus h to c plus h. If you are considering it from c minus h to c plus h, in this width f of c is greater. So we can say c is the point of local maxima and f of c is the local maximum value. Right. So this is the definition for local maxima. And the definition for local minima, what you have to do is C is called point of local maxima. You can change this to local minima. If there exists an h greater than 0 such that f of c less than, you can change this greater than, you can change it into less than. Okay. In f of c is less than f of x for all x in c minus h, c plus h, then therefore local minima. Here you have to write local minima. So this is the definition for local minima. Okay. Now also you note down that that I will tell you later. There's an important point that I'll tell you later. Okay. So after this, now let's go to the first derivative test. That how will we find the local maxima and local minima? Right. We have two methods to find the point of local minima and local maxima, which is first derivative test and second derivative test. In the last class, we already explained what is first derivative test. Now we are going to explain what is second derivative test. This is second derivative test. Let f be a function which is twice differentiable at c. Then c is a local maxima if f dash of c is equal to 0 and f double dash c is less than 0. So f be a function which is twice differentiable at c. So twice differentiable at c means the second derivative is defined. So a second derivative is defined at c. That is what twice differentiable at c means. Okay. So and if the c is local maxima, if derivative at c is equal to 0, at c the derivative is equal to 0 and second derivative is less than 0. This means the second order derivative at the point c is a negative value. This is second derivative test in which we will find second derivative. Right. So the working rule will be, suppose you have a function f of x. This is the working rule. Suppose you have a function f of x First, you have to differentiate it, find f dash of x, equate it with 0 to find the value of c. Okay. You have a function, you differentiated it, you got x equal to c. C is the point where the derivative is equal to 0. Now you have to check whether the point C is a local maximum value or a local minimum value. For that, you need to find the second derivative. You have to differentiate it again. You have to find f double dash of x. Now, you have to check whether this f double dash of x is negative or a positive value. But you have to substitute the c, find f double dash c, find f double dash c. If f double dash c is negative value, means if it is less than 0, then c is locally maximum. Okay. If second derivative gives you a negative value, then it is local maxima. If second derivative gives you a positive value, then it is local minima. So the definition of local minima will be, you just have to change here, instead of maxima you have to write minima if f dash c equal to 0, and f dash of c, instead of less than 0 you have to write greater than 0 if it is minima, right? And if f double dash of c is equal to 0, f double dash at c, if second derivative is equal to 0, means it is not positive neither negative. If it is equal to 0, f double dash c equal to 0, then that means the second derivative test fails. Okay, you have to go back to first derivative test, which we learned in the last class. If this is equal to 0, second derivative test fails. Okay, and then this point C may be point of inflection, but that you can't find in this method. You have to find out in the first derivative method if f dash of c is equal to 0. Okay, now let's do some problems from this local maxima and local minima. Right. Let's do a problem. Suppose f of x is equal to x cubed minus 3x plus 3. We need to find a local maxima and local minima of this function. For that, the working rule is by second derivative test. For that, the working rule is first you have to differentiate this function, equate it with 0, solve to find the point of local maxima and local minima, and check whether which point is local maxima and which point is local minima by finding the second derivative. Okay, so first step is to differentiate. So f dash of x is equal to 3x square minus 3. Okay, next to equate this with 0. So f dash of x 3x square minus 3 equal to 0 means x is equal to plus or minus 1. Okay, so we got 2 points, x is equal to 1 and x is equal to negative 1. So you need to find which one is point of local maxima and which is local minima. For that we have to find the second derivative of the function. Since this is f dash of x, the second derivative will be f double dash x is equal to derivative of 3x square, which is 6x. Okay, now f double dash of 1 is 6, which is greater than 0. We just need to write the simple f double dash of 1 is greater than 0. We just need to write the sign. Okay, and f double dash of negative 1, that will be 6 into negative 1, which is less than 0. Okay, this is 6, which is greater than 0, and this f double dash of negative 1 is minus 6, which is less than 0. So the second derivative is positive, is greater than 0 at the point 1 and less than 0 at the point negative 1. That means as negative 1 is point of local maxima and 1 is point of local minima, and 1 is the point of local minima. Since negative 1 is the point of local maxima, and the local maximum value of the function is f of negative 1. Substituting this point of local maxima as the function, you will get the local maximum value. So the local maximum value is negative 1 the whole cube minus 3 times of negative 1 plus 3, which is negative 1 the whole cube is negative 1 plus 3 plus 3. Okay, so 3 plus 3, 6 minus 1. The 5 is the local maximum value. Like that, if you want the local minimum value, you just substitute 1 at the place of this. So f of 1, this is local minimum value. This is local maximum value. Local maximum value is this. Okay, local minimum value is f of 1. Okay, minimum value. Local minimum value. F of 1, which is 1 minus 3 negative 2 plus 3 is equal to 1. So this is the local minimum value and this is the local maximum value. This 5 is the local maximum value. Okay, now let's go to another problem. Okay, but the questions of 6 marks won't be like this. A function like this won't be provided. A function in the form of f of x won't be provided. You have to derive a function according to the situation. Okay, let's check out. This is question number 21 of page number 233 of exercise 6.6. The question is, of all the closed cylindrical cans of volume 100 cm cube, find the dimensions of the can which has minimum surface area. So we have a cylinder here whose volume is fixed. Volume is constant 100 cm cube. So volume of the cylinder is 100 cm cube. So you can make cylinder in any dimensions, like the cylinder can be like this. Okay. The volume should be 100 for this cylinder or this cylinder. The volume should be 100, and you can make the cylinder like this, with a greater radius and a lesser height. Okay. So you can change the radius and height in such a way that the volume always remains a constant, which is equal to 100. But the surface area of all these cylinders will be different. Even if the volume is 100, the radius and height are changed, balancing the volume equal to 100, but the surface area will be different. So you want to find the dimensions, means the radius and height at which the surface area is minimum and volume still remain 100. So what we can do is, we can change radius and height, but the volume should be 100. Okay, so what you have to do is, you have to minimize the surface area. Okay, if you want to minimize the surface area, you have to find the point of minima of the surface area. That means, here the function is surface area. You have to differentiate the surface area. So let's write what is the equation for surface area. So surface area of the cylinder. The surface area means it includes this curved and the base, which is circles. Okay, so total surface area is equal to 2 pi r h, which is curved surface area, plus pi r square. So 2 pi r h plus pi r square. This is the equation of surface area. And you can clearly see that in the surface area, now this is not a function of radius or a function of height, since this consists radius and height. Okay, the function is not in the form f of x, y equal to f of x. The function is not in the form y equal to f of x. So you have to simplify this in such a way that this is in the form y equal to f of x. Means it should be depend only on a single variable. This should depend on either r or h, not in both terms r and h. See, it is given that the volume is 100 centimeter cube. That means volume means pi r square h, which is equal to 100. From here you can find h is equal to 100 by pi r square. So h is equal to 100 by pi r square. Now we can substitute this h over here. Okay, then that equation will become in terms of radius only. Let's see. So surface area S in terms of radius r will be 2 pi r into 100 by pi r square plus pi r square, right? 2 pi r into 100 by pi r square plus pi r square. Now the surface area is only in terms of r. Now you can say the surface area is in the form, this is in the form y equal to f of x. Like S is equal to a function of r, a function of r. Surface area S is equal to in terms of a function of r. We can simplify this radius, okay, and we can also simplify this pi. Now 200 by r is plus pi r square. S of r is equal to 200 by r. S of r is equal to 200 upon r plus pi r square. This is the function. Now you have to differentiate this, equate with 0, find the local maxima, find the second derivative. You can use second derivative test or first derivative test, but second derivative test, which we learned last time, will be comfortable for this type of distance. Okay, so s dash of r, the derivative will be equal to 200 by r. Derivative of 1 by x, you know d by dx of 1 by x is negative 1 by x square. So derivative of 200 by r will be negative 200 by r square plus derivative of pi r square will be 2 pi r. Okay, now you have to equate this with 0 because at minima or maxima the first derivative will be equal to 0. That means you can take this negative 200 by r square to right side. That makes this 2 pi r is equal to 200 over r square. Now you can cancel this 2 here to be 100. That means r cube is equal to 200 by r cube is equal to 200 by 100 by pi. R cube is equal to 100 by pi. I think I have made a mistake here. 2 pi r. Okay, here it is 2 pi rh plus 2 pi r square, not pi r square, since we have here two circles on upper and lower part, right? So I'm sorry, I had made a mistake here. The surface area is 2 pi rh for the curved surface and 2 pi r square for the base areas. So here will be a 2 pi r square. So here will be into 2, here into 2. So this will make this 4. So here 2 and 2 will be cancelled. Again there will be a 2. So r cube will be equal to 100 by pi, not 100 by pi. Here will be a 2. So r cube will be equal to 50 by pi. Okay. So r cube is equal to 50 by pi and r equal to under cube root of 50 by pi. Now we got the value of r when the derivative was equal to 0. We just equated the derivative with 0, okay, and we got the value of r. Now we have to make sure that this r is point of local minima, since we have to find the minimum surface area. Okay. So in order to make sure that, we have to differentiate this again. You have to find the second derivative, and the second derivative s double dash of r, second derivative will be, so second derivative of this function minus 200 by r square, and derivative of 1 by r square is minus 2 by r cube. So this will be 400 by r cube. Okay, again derivative of 4 pi r will be 4 pi. Okay, so you need to prove that this is greater than 0, and you can clearly see this is greater than 0 if you substitute r is equal to this is cube root, right? Since here is cube, this is cube root. R is equal to cube root of 50 by pi is point of local maxima. Since this gives always a positive value, here there is no negative sign, so this always gives a positive value, right? That means r equal to cube root of 50 by pi is local minimum. Okay, that means this surface area is minimum when radius is equal to cube root of 50 by pi. Now what you have to find is you have to find the dimensions. Dimensions means you have to find the radius and height. So you need to find the height of the cylinder. Okay, and height, it is given that height is equal to 100 by pi r square. So height is equal to 100 over pi into r square, r which is this, cube root of 50 by pi. So cube root of 50 by pi. Okay, and this whole square, right? R square, r is this. So cube root had written an exponent form like raised to 1 by 3, and you have to square this, and this will make this raised to 2 by 3. Okay. So 100 by pi, you have 100 by pi into 50 by pi whole raised to 2 by 3. Now you can simplify this. So I am writing this 100 as 50 multiplied by 2 in order to simplify this, and here it will be a pi 50 to the power 2 by 3 divided by pi to the power 2 by 3, and cancelling this 50, this is 50 raised to 1, cancelling 50 and 50 raised to 1 and 50 raised to 2 by 3, 1 minus 2 by 3 will be 1 by 3, and pi to the power of 1, pi to the power of 2 by 3. Simplifying this, you'll get pi raised to 1 by 3. So your answer will be 2 times 50 by pi whole raised to 1 by 3. Right? 1 minus 2 by 3 is 1 by 3. Again, the power of pi, which is 1 and 2 by 3. So 1 minus 2 by 3 is again 1 by 3. So this is the answer. 2 times of 50 by pi raised to 1 by 3. This is the height. Okay. And this is the radius. So dimensions are radius, which is cube root of 50 by pi, and height, which is 2 times of cube root of 50 by pi. Okay. Now let's move to the next question. So next is question number 19. Of all the rectangles inscribed in a given fixed circle, prove that the square has maximum area. So imagine a circle and there is lot of rectangles, means infinite rectangles in the circle. Okay, there is lot of rectangle. You can, I'm drawing another figure. Okay, this is a rectangle, this is a rectangle. So this is also a rectangle. That means the length and breadth of this rectangle is changing, but the radius is fixed, since this is a fixed circle. Okay. So you read this as circle and this as square. Okay. Okay, you need to prove that the area of this rectangle is maximum when this rectangle is square. That means the length, the area is maximum when length is equal to its breadth. See here, the length and breadth of this rectangle is changing. First, it was this was length and this is breadth, and it is changing in if we draw a lot of rectangles, infinite rectangles. But we need to prove that the length is equal to breadth when the area is maximum. So we have to maximize the area. Okay, let's write the equation for area. So area is equal to length into breadth. Let x be the length and y be the breadth. So area is equal to length into breadth means area is equal to x multiplied by y. We need to differentiate this x into y. This is a function, but this function is not in the form y equal to f of x. This function, in this function, there is two variables x and y. Both are variables. Both varies. Both changes. Right? X and y changes. X can't change independently. If x changes, y also changes. You can clearly see that. If length changes, the breadth also changes. Okay. So we need to derive this function in the form of f of x. That means either we have to eliminate this x or y. Okay. For that, we have to derive a relation between x and y to eliminate this. See, here the radius of the circle is fixed, means this will be, if this is the diameter, this will be the diameter. Since this angle is 90 degree, we know the angles of semicircle is 90 degrees, so this will be a semicircle, and hence this is diameter. And also this is the diagonal of the square. And here we have a Pythagoras relation, which is x square plus y square is equal to 2r whole square. Right? X square plus y square equal to 4r square, and y, this is 4r square. So y square equal to 4r square minus x square. So we can use this relation, okay, over here. And you can, if you wish, you can write y is equal to under root of 4r square minus x square, square root of, and we can substitute here root 4r square minus x square. But for our convenience, let's square the area. So area square will be equal to x square into y square, area square. Why we are doing that? Because if there is a square root, it will be difficult to differentiate. And we have to prove the area is maximum. Okay, we have to prove the area of the rectangle is maximum when it is square. If area is maximum, area square is also. That if area square is maximum, we are going to prove the area square is maximum, and if area square is maximum, area will be also maximum. Okay, so we are taking area square as the function. Okay, now we can substitute this y square minus 4r square over here. So this is equal to x square into 4r square minus x square. Now multiplying x square inside, this will become 4r square x square, 4r square x square minus x to the power of 4. So this is our function. Let's write this as f of x. Now this is in the function in terms of x only. So f of x is equal to 4r square x square minus x raised to 4. This is, we got the function in terms of x only. Now we'll differentiate this, equate with the 0, solve this, and we'll find the point of local maxima. So let's differentiate this. So f dash of x is equal to derivative of this, x square derivative is 2x. Never try to differentiate 4r square since 4r square is a constant. R is a constant, you can clearly see that r doesn't change. X and y can be changed, but r is fixed, r does not change, right? Since this rectangle is inscribed in this fixed circle. So r is a constant, there is no derivative for that. Okay, there is no rate of change for that. R never changes, so there won't be any rate of change. So 4r square is constant, multiplying this derivative of x square, which is 2x. So 4r square into 2x minus derivative of x raised to 4 is 4x cubed. So derivative is over. Let's equate with 0 and solve this. Okay, let's take 4x cubed to this side. So 4r square into 2x is equal to 4x cubed. Cancelling this 4 and 4, and this x cubed and x, what remains is 2r square is equal to x square, and x is equal to root 2r. Okay, now we need to prove that x is equal to root 2r is point of local maxima of this function, since we need maximum area. So in order to find local maxima, we'll differentiate this function again. Okay, we'll find the second derivative. So f double dash x. Okay, f double dash x is equal to so f double dash x is equal to 4 into 2, 8r square x, 8r square x minus 12x square. So we got second derivative. We need to prove that the second derivative gives us a negative value on substituting x is equal to root 2r. So if we substitute x is equal to root 2r, this will become f double dash x is equal to 8r square x minus 12 into x square means root 2r whole square, which is 2r square. So 8r square, so I think here won't be x, right? 4r square into 2x, 4r square derivative of 2x is 2, right? So here won't be x. Sorry, my mistake. So 8r square minus 12x square, and 8r, so here won't be x, right? So 8r square minus 12 into r square, which is 24r square. So 8r square minus 24r square will be negative, less than 0, right? 8r square minus 24r square will be a negative value. So x is equal to root 2r is point of maxima. The x is equal to root 2r is the point of local maxima. No, point of local maxima. So it means that the area square is maximum, or the area is maximum when the length is equal to root 2r. But what we have to prove is, we have to prove that rectangle is a square. For that we need to prove length and breadth both are equal. X is equal to y. Let's check what is the value of y. And we have written here y square equal to 4r square minus x square. So y square is equal to 4r square minus this x square. X square means 2r square. So 4r square minus 2r square, which is equal to 2r square. So y square is equal to 2r square. That means y is also is equal to root 2r. So x is root 2r, and we got y is also equal to root 2r. That means x and y are equal, this rectangle is a square when the area is maximum. Now let's move to the next question. The next question is question number 23. This is question number 23. Okay. Prove that the volume of the largest cone that can be inscribed in a sphere of radius r is 8 by 27 of volume of sphere. So we have a sphere of radius r. Radius r means radius is fixed. Radius is given r, capital R. So we have a fixed sphere. Okay. And there is a cone inscribed in this sphere. Okay. So we need to prove that the volume of the largest cone. So largest cone here means the cone with the maximum volume. So the volume of the cone is maximum. We need to prove that the volume of the cone will be equal to 8 by 27 times volume of the sphere. Okay. Prove that the volume of the largest cone. That means the cone with maximum volume. So prove that the volume of the largest cone, the maximum volume of the cone, that can be inscribed in a sphere of radius r. That means in a fixed sphere, the volume of the cone will be equal to 8 by 27 times volume of the sphere. So here we have to maximize the volume of the cone, volume of the largest cone. That means maximum volume. Okay, so we need to maximize the volume of the cone. For that we need to find the point of maxima, local maxima of the cone. What is the volume of the cone? So equation to find the volume is pi by 3 r square h. So this is volume of the cone. And here we have two variables, radius and height. The volume is depending on radius and height. This function is not in the form of f of x. Means that it is not in the form y equal to f of x. This is depending on radius and height. Radius and height both are variables. See, this is radius and this is height. Okay, this is the height of the cone. Both are variables. Okay, radius and height can't change independently. If radius changes, height also changes. You can clearly see that from the figure. And the constant is this radius of the sphere. But the capital R, which radius of the sphere, is fixed. Okay, so you have to eliminate either this radius of the cone or radius of the height. For that, we have to derive a relation between the small letter r and small letter h. So we can derive that relation geometrically, like this will be capital R, the radius of the sphere. This is radius of the sphere. Okay, and this is small letter r, which is radius of the cone. This is h, means this is the height of the cone. Okay, this completely is h. This is also equal to r. This from the center to till here is also equal to r. That means this part will be equal to the h minus, this is h and this is r, so h minus r. So this is h minus r. So here we can derive the Pythagoras relation, like r square is equal to, this r square equal to r square, capital R square, minus h minus r whole square. Okay, if we expand this, we will get r square equal to r square minus h square plus 2hr. Since I am distributing this negative into the bracket, so that's why negative 2hr become plus 2hr, and minus of minus r square will be positive r square, right? Sorry, negative r square. Since here we have a capital R square, so positive r square, and this. Okay, now this r square and this minus r square will be cancelled. What remains is 2hr minus h square. This r square is equal to 2hr minus h square. And now we can substitute this r square 2hr minus r square in at the place of r square. So volume equal to pi by 3 into 2hr minus h square the whole into h. Okay, now this function, the function of volume function, only depend on h. Since this capital R is a constant that doesn't changes, right? It doesn't change. The sphere is fixed, so capital R never changes. So this depends only on h. So we can write this as volume in terms of h means V of h. This is a function. So we can multiply h inside. So this becomes pi by 3 into 2rh square. So 2 and r are constant. H into h square minus h cube. Now this is the volume in terms of h. Now we got the function. We got the function V of h is equal to this. We got in the form of y equal to f of x. Right. Now we have to differentiate this point of maxima, second derivative and all. Okay. So v dash of h, the first derivative is equal to pi by 3 into, so derivative of h square is 2h, so 2 into 2 which is 4rh minus 3h square. Since derivative is 0 at maximum volume, so we can equate the derivative with 0 and can solve this. So 4rh minus 3h square is equal to 0. That means 4rh is equal to 3h square. If this is equal to 0, we can take 3h square to this side. Okay, so cancelling this h and h, we will get h is equal to 4r by 3. H is equal to 4r by 3. Now we need to prove that h is equal to 4r by 3 is the point of local maxima. For that, we'll go for second derivative, v double dash h. Okay, so second derivative of this. So pi by 3 into, in bracket, 4rh. We are differentiating this with respect to h. So 4r minus derivative of 3h square, which is equal to 6h. So this is second derivative. We need to prove that second derivative is negative when h is equal to 4r by 3. In order to get this is local maxima. So let's substitute h is equal to 4r by 3. So v double dash h will be equal to pi by 3 into 4r minus 6 into this 4r by 3. 4r by 3. So cancelling 3 and 6, you will be 2 into 4r, which is 8r. So 4r minus 8r is less than 0. 4r minus 8r is negative 4r, which is less than 0. So this is v double dash h is less than 0 when h is equal to 4r by 3. That means h equal to 4r by 3 is point of maxima. Okay, that means the volume of the cone is maximum when height is 4 by 3 times of the radius of the sphere. But what we have to prove is, we need to prove that the volume of the cone is equal to 8 by 27 times volume of the sphere. Okay, volume of the cone means this is equal to 8 by 27 times volume of the sphere, means we have to get volume of the cone is equal to 8 by 27 times 4 by 3 pi r cube, capital R cube, because 4 by 3 pi r cube is the volume of the sphere. Let's see how we'll prove that. So h is equal to 4r by 3. Okay, now we have to find the maximum volume of the cone. So how will we get maximum volume of the cone? We'll get maximum volume of the cone if we substitute h is equal to 4r by 3, since this is the point of local maxima of the volume. This is point of local maxima. So in order to find the maximum volume, we have to substitute h is equal to 4r by 3 at the place of h. And let's use this formula. Since volume is equal to pi by 3 r square h, and in this situation, if the cone is inscribed in the sphere, we can take this equation, right? This is also equation for the volume of the cone. If the cone is inscribed in this sphere, and this equation is in terms of height and capital R. That's why I am selecting this equation. If I am selecting this, here it will be r square, and again for r square we have to use this relation. Okay, well we have to reach here 8 by 27 into 4 by 3 pi r cube. Keep this in mind. We have to reach here in order to prove this. 8 by 27 to 4 by 3 pi r cube. So in this relation which we have to prove, there should only capital R. So for h we can substitute 4r by 3, and for r square we have to again go to this relation. But instead of that, we can use this relation of volume of cone. That will be easy. Okay, so volume of cone. So volume of cone, or we can write maximum volume of cone. So maximum volume of cone is equal to, okay, pi by 3. Why maximum volume? Because we are substituting the point of maxima here. So pi by 3 into 2r, instead of h square you can write the square of this, which is 16 r square. So r square makes this r, this will be r cube, right? Well, I am substituting here 4r by 3. So 4 square 16, 16 r square. So there were already a r, that's why this becomes r cube. So divided by 4 square of 4r by 3 whole square. So denominator will be 9. Minus h cube. H cube means h is 4r by 3. So cube of this. Cube of this means 64 by 27 r cube. So 64 by 27 r cube. Okay, so this is the volume of the maximum cone. Now we can simplify this. We can take, since here r cube and r cube is common, 2 into 16, 32. 32 is also common since 64 is 32 into 2. And 9 is also common. So what we can take in common is pi by 3. This is pi by 3. Then 32 r cube divided by, okay, 32 r cube divided by, taking 9 also, so divided by 9. This is common. So here what remains is 1, just 1. 1 minus here, what remains is, since 32 taken from here will be 2 and denominator there will be 3. So 1 minus 2 by 3 remains in the bracket. And 1 minus 2 by 3 is equal to 1 by 3. So pi by 3 into 32, I am writing the 32 as 4 into 8 in order to prove that, in order to get 8 by 27. Okay, so 4 into 8 and 3 into 9, I am writing this as 27. Okay, 27, 3 into 9 is equal to 27 into, and 1 minus 2 by 3, and r cube is here, right? R cube into 1 minus 2 by 3, which is equal to 1 by 3. So 8 by 27, if we keep 8 by 27 aside, 8 by 27 into 4 pi r cube by 3. Okay, 8 by 27 into 4 by 3 pi r cube. That means 8 by 27 into the volume of the sphere. Okay, 4 by 3 pi r cube, you can write this is the volume of sphere. So we got 8 by 27 into 4 by 3 pi r cube. 8 by 27 to volume of the sphere. The maximum volume of the cone is equal to 8 by 27 times the volume of the sphere. Okay, now we'll move to the next question. So the next question is, prove that the semi-vertical angle of a cone of maximum volume and given slant height is tan inverse root 2. The semi-vertical angle. So what is semi-vertical angle? Suppose this is a cone, then this angle is this angle is vertical angle. Semi-vertical angle means half of this, which is this angle. Okay, so this angle is semi-vertical angle. So we have to prove that this angle is tan inverse root 2. If this be theta, we need to prove that tan of theta is equal to root 2. That means theta is tan inverse root 2. So we need to prove if this angle is theta, we need to prove that tan theta is equal to root 2. That is what we have to prove. If the volume is maximum and slant height is given, that means on a fixed slant height, on a constant slant height. So here slant height is constant, L is constant. Slant height, we use the letter L, right? So this is slant height, this is height, and this is radius. Okay, so what you have to maximize is maximize the volume. So we need to differentiate the equation of volume. Okay, so volume of the cone is equal to 1 by 3 pi r square h. We need to differentiate this, but here we have two variables, radius and height. So we can eliminate either radius or height. We can use the connection L square is equal to h square plus r square. So instead of r square, we can write L square minus h square. Okay, so this becomes pi by 3 into L square minus h square the whole into h. Okay, so this is volume of cone. Okay, so now let's simplify this. We can take h inside, so this becomes pi by 3 into L square h minus h cube. Okay, so this is the volume of cone. Now we have to do volume of cone. So volume of cone, now it is in terms of h only. So you always make sure that the function is in the form y equal to f of x. Means it is in explicit form, not in terms of not like x and y are mixed together. This is right. This is like volume in terms of h only, right? This L is just a constant. Okay, so in all these questions, what we have done is we have derived the function in terms of y equal to f of x, and always there were two variables like radius and height. If you go to the previous examples, there were always two variables, and what we have done is we just eliminated one variable with the help of the relation. There will be always a relation. There will be always something which is constant. So we use that constant. We will derive a relation between this two variable and the constant. Then we'll derive the function in the form of only one variable like this. Now what we can do is we can differentiate, find point of local maxima, second order derivative, all those steps. So v double dash not c, v double dash h. This is the terms of h. So v dash h, first derivative, v dash h is equal to pi by 3 into L square. We are differentiating it with respect to this variable h. So L square minus 3h square. Okay, so we are equating this with 0 since volume is maximum at derivative when the derivative is 0. So L square is equal to 3h square and h is equal to L upon root 3. We need to prove that this L by root 3, h is equal to L by root 3 is point of maximum. For that we are going for the second derivative. V double dash h is equal to pi by 3 times the L square derivative will be 0 since it is a constant and there is no term with h with this h L square. So derivative of this constant L square will be 0 and 3h square derivative will be negative 6h. We need to prove that second derivative is negative, and you can see that this is negative, right? 0 minus 6 means is negative. So it is negative. We need no need to substitute L by root 3 here. It is already negative. Okay. So V double dash h, second derivative is negative. That means h is equal to L by root 3 is point of maxima. Okay. H is equal to L by root 3 is point of maxima. But what you have to get is we have to prove that this angle is tan inverse root 2. That means tan theta is equal to root 2. This is what we have to prove. Okay. So tan theta means r by h. So we need a relation between r and h to get tan theta is equal to root 2. Okay. Now what we got is a relation between h and L, but we need a relation between r and h to derive an expression for tan theta. Okay, so r by h. Okay, we know that L square, if h is equal to L by root 3, then if we square this and taking root 3 to this side, we will get L square equal to 3h square, right? So L square is equal to 3h square. L square is equal to 3h square. When the volume is maximum, h is equal to L by root 3, that means L square is equal to 3h square. And L square equal to h square plus h square. So h square plus r square is equal to 3h square. That means 2h square is equal to r square. Or taking square root on both sides, you will get root 2h is equal to r. Okay, root 2h is equal to r. Now from the figure, tan theta is equal to radius over height. So we can substitute radius is equal to root 2h. So you will get root 2h upon h. We cancel this h, we will get this is equal to root 2. Tan theta equal to root 2. Okay, so theta is tan inverse root 2. Now we just proved that semi-vertical angle is tan inverse of root 2. Okay, theta equal to tan inverse root 2. This is done. Okay, so I have done few questions on this. You can do the rest of the questions and send to me. If you have any doubts, you can ask me doubts, or you can ask doubts in the comment section, or you can just WhatsApp me. This is my WhatsApp number. So if you have any doubts, you can WhatsApp me on this number, right? So see you in the next class. Bye. Hey, one second. In the next class, we will be discussing about absolute maxima and absolute minima. From till now, we just discussed about local maxima, local minima, and we said about the point of inflection Now we have next class we will be discussing about absolute maxima, absolute maxima and absolute minima. Okay, see you in the next class. Bye.